Go, go. Here we go. Starting in now. Hey, everybody. Welcome, welcome. We're looking at page 958. Yesterday we learned about derivative rules. So we have some shortcuts, so we don't have to use the formal definition of derivatives to find these anymore. And we also are able to find antiderivatives, all right, which is kind of doing the opposite of what we're doing. So if I want to find the derivative of this, first of all, I actually need to make sure that it's expanded properly. And I guess I could do minus b. Oh, wow, come on. Seriously? Here we go. All right. Whew. I was going to say a little undo pinwheel of death. Yikes. So a minus b all cubed is the same as a cubed minus 3a squared b plus 3ab squared minus b cubed. All right, so it's just really a matter of a lot of the algebra here that we got to do. So f of x, if I expand this, should be 3x all cubed minus 3 times 3x squared times 4. I've already accounted for my negative in the formula here. Plus 3 times 3x times 4 squared minus 4 cubed. So let's simplify this further. So this would be there we go. Yeah, it's lagging. 27x. Come on now, computer. Cubed minus. Let's see, 3 squared is 9, times 3 is 27, times 4, 7 times 4, 28, plus 80, 108. Is that right? X squared, I believe. Plus 4 squared is 16 times 9, 16 times 9, isn't that 144? Am I right? Yeah. X, and then minus 4 cubed is minus 64. So here's f of x. So if I want to find the derivative of f of x, I'm essentially going to be multiplying my coefficients by the exponent and decreasing the exponent by 1. Am I right? I believe. So the derivative of this, I would do 3 times 27 is 81x squared. Right? And Uncle Dan, D-A-N-N, would be proud. Minus 108. I don't know. I'm not sure if having you guys harass my uncle is a good idea. He's a good guy, though. So double that, reduce the exponent by 1 is 1, right? And then this one would just be plus 144, x to the 0th. And the derivative of a constant is always 0.
Oh, Mr. Lottie?
Yes.
In mine, I didn't show the step where I do like n plus 1 or whatever.
Yeah,
I just
that's fine.
put in what n plus 1.
Yeah, I added it. I even skipped it here as well. For the notes, I decided to write that a little bit different just to make sure that in our notes we had an example. So there's the derivative of that. Not too shabby. So how about some other questions? 31 and 33. How about I do one of those?
Yeah, I don't know how to do it.
Let's do 31. I think that's actually a little bit... Well, no, 33 might be a little bit more interesting. Hello.
Sorry.
No problem.
Can we wait at the elders for 5 minutes?
Absolutely.
Sorry.
No problem. No problem. So, so here we go. I just did a sideways smoosh there, horizontal. So if I want to find the derivative of this, first of all, I'd expand it. So that's the same as x squared minus x minus 2, I believe, when I FOIL it all out and combine my like terms. And check this out, y prime. That's right, you can use that notation as well when it's not written just in terms of f of x. Is going to be 2x minus 1. So the instructions here, they actually wanted to find the slope of the tangent line for x equals 1. So if I want to do that, all I have to do is plug in 1 into the derivative, and I would have y prime is equal to 2 times 1 minus 1, which is 2 minus 1, or 1. So that's the value of y prime, meaning that at x equals 1, the slope for the original function happens to be 1 in this case. Okay. So the derivative represents the slope of the original function at any given point. Actually, sometimes it'll even be referred to as the instantaneous rate of change. All right, the slope for that very instant, that single point, how steep the curve was going at that moment. So instantaneous rate of change is another way you'll hear that phrased. Right? Actually, let's expand this question. Little expansion here. What if I wanted to know what rather is the minimum of y for this function y? How could I find that out? How could I find the minimum value of this function? What's the slope of the tangent line at a critical point? At a extrema, 0. So what I could do is I could set y prime equal to 0. Sure.
Oh,
So when is 2x minus 1 equal to 0? So when is 2x equal to 1? When is x equal to a half? So x equals a half is the x-coordinate of the minimum point of my original function. I knew that because I was able to set the derivative to 0 and solve. And then if I want to find the actual minimum value of that, I could plug in a half in either of the forms for y. So y equals, I guess I'll do this one, 1/2 plus 1 times 1/2 minus 2. It's probably a little bit more punishing than the other version. So that's 1.5 or 3/2 times 1/2 minus 2 would be minus 3/2, I believe. Am I right? I think. Yeah, I'd say so. And multiply across, so negative 9/4 is actually the y value, the minimum that I end up getting. So that's a general theme that we can get if I'm looking for the extrema of a function. I can take its derivative and set its derivative equal to 0, and that will give me all of the x-coordinates of its extrema. Okay? So it's just little bonus content, director's cut, extended edition. Right. And let's see, I'm going to be setting up, and then what's the last problem you wanted me to do? 43?
Well, now that I don't know how I missed the whole answer.
Well, that's okay. Well, I still can do it out. I mean, because people on the internet might not have noticed. 44 is an interesting one as well. I could do 44 for funsies. I think I'll do 43, though, just so I get a sample of that, because we need some antiderivative practice as well, don't we? All right, I'm just going to grab a snapshot of this, and 43. So it says, find the antiderivative. Okay. So how would this function relate to the antiderivative? Right, we're trying to find the antiderivative, but what does this function represent on the antiderivative?
The derivative
It's the derivative of the antiderivative. So therefore, this must represent what?
the original function.
No? Well, in this case, I guess it's the original function when I'm finding the antiderivative. But what does this represent of the antiderivative? This function represents something. If it's the derivative, what does it represent? It represents the slope of any tangent line on the antiderivative, right? And because it represents the slope of this other unknown function, the height of this other function actually doesn't matter, because this one, all we know is the slope. We don't know the y-intercept. We don't know the height of it. Question, comment?
Using that, couldn't we find what the original line was, plugging in x value?
What the original what was?
What the original line, what the antiderivative of that is, using that formula, plugging in x values.
Plugging in x values would give me the slope of all those points. I mean, I could plug in some x values and be like, here the slope was that, here the slope was that, here the slope was that, and then try to like figure out what that curve would have looked like over time. There is actually a thing called slope fields in calculus where you're able to kind of like, it almost looks like this weird little like flow chart of a river flowing through a coordinate plane, where at every point on the coordinate plane it's got a slope representing. It's weird, but anyways, let's look at this one. So here's f of x. The thing I'm going to do is whether you cancel one x out of all three terms or factor out an x and then cancel, either way is fine. But we're going to cancel this out, so I'll get f of x equals x squared plus 4x plus 1, right?
I basically just write equals x squared plus 4x plus 1.
However, there is still an additional fact about this that I should be aware of, which is x cannot equal what?
0.
0, okay? So it looks exactly like this parabola, just with a hole in it, okay? So is this a continuous function?
It can be 0 because...
No,
Oh, right,
the
yeah.
original variable.
Yeah, I was looking
So-
at
So even though I simplified this, it still has the domain of the original where x could not equal 0. All right? So is it continuous at x equals 0?
No.
No. Why? What part of the continuity? It fails part 1 of the continuity test.
And
Would it
part
pass?
3.
Would it pass part 2?
Yeah.
Yes.
Yes, because it would be a smooth parabola with just a hole in it, so it would be approaching the same value
Then
from left
it
to
would
right.
automatically not pass part 3 because there
Correct.
is no f of c to approach.
Precisely. Would the limit exist at x equals 0?
Yes.
It would, because it's approaching the same value from both sides, even though there's a hole at that value. And the limit is not concerned what it's equal at that value, it's concerned with what the graph is approaching. So a limit does not have to pass. If I'm taking the limit, I'm not concerned about part 1 of the continuity test at that particular value. I'm really just kind of concerned about part 2 of the continuity test in some regards. But I'm not here to find the limit or the continuity. I'm here to find cap f of x, which is the antiderivative. And the way I do that, what am I going to do with this coefficient? I'm dividing by the exponent plus 1, right? Then multiplying by x to the exponent plus 1. Right? 1 over n plus 1 times x to the n plus 1th. And for this next one, I would have plus 4 over 1 plus 1, because this exponent was 1, right? Times x to the 1 plus 1th. And then I would have plus, what would
0 plus 1.
X.
1 over 0 plus 1 to the x to the 0 plus 1.
Not
You
to
mean
the
times
x,
x to the 0 plus 1?
It's times x.
Yeah, sorry, times, yeah.
Plus C.
And then plus c, because there's some constant value that I could have taken the derivative of that would have brought me back to a plus 0, okay? And I don't know what that value would have been. That's an unknown to me, but that's okay, because we had an equation that represented only the slope, and the slope would be the same for this function or any function that's been shifted up or down by any number of points, right? The slope still would be unaffected by that constant. So let's simplify this. So I'll get cap f of x is equal to 1/3 x to the 3rd plus 4 divided by 2 is 2x squared plus x plus c, and I believe we'd still have the limited value of x cannot equal 0. Actually, that means, well, actually, if the derivative was undefined at x equals not equal to 0, all right, at x equals 0, the derivative is undefined. That means the slope of the original function, or the antiderivative in this case, sorry, is undefined at that point. What's an undefined slope look like? It's vertical. Yeah. So this one actually is interesting. It's possible there could have been a point of inflection at that. Yeah. The book's answer actually is just this, where it doesn't consider
Where x is not equal.
where x does not equal to. But it may have been a point of inflection where it could have been like something like this. Nope, not quite. Like this. Where for a moment maybe it hits exactly a vertical slope and then it leaves it right away. So it's not asymptotic, but it just for a moment had an undefined slope. But either way, this is the answer. This one would be interesting as far as the domain and everything takes into effect. But anyways, I think that covers most everything about our derivatives, antiderivatives. Derivative represents slope, blah, blah, blah. All right. Goodbye, Internet.